Hello, everybody. My name is Robert Wille, and I'm with the Johannes Kepler University in Linz and CSO of the Software Competence Center in Hagenberg, both in Austria. And in my talk, I would like to briefly give you an overview on design automation for reversible and adiabatic circuits. And before I start, let me make a confession first. I'm actually not an expert in the physical design of reversible and adiabatic circuits, particularly not in the physical implementations of those technologies. I consider myself an expert in design automation, and that's what I'm doing research in. That means once we have proper models, proper objectives, proper constraints, we can develop corresponding design automation tools for that. And it's basically what I've done in the task, and that's basically what I would like to briefly introduce you in this talk here. So in the next 20 minutes, I would like to give you a rough overview what we have done so far in reversible circuit design and initial ideas towards adiabatic circuit design. And all of that should be seen as a starting point for the discussion so that we maybe can, develop further how future tools for design automation of reversible adiabatic circuit should look like. And to do that, I structure my talk into two parts. In the first part, I'm going to talk about reversible circuit design. And in the second part, I'm going to talk about first ideas towards adiabatic circuit design. So let me dive directly into that, design synthesis of reversible circuits. The major challenge here is, of course, that in many cases, we want to realize a non-reversible function, for example, an AND function as shown here, in terms of a reversible circuit. That means the first step we have to do is we have to map, or we have to transform the originally given function into a reversible function, a step which is usually called embedding. And once we have that, then we can, our aim is to generate a corresponding reversible circuits. And in most of the cases, as you know, we are usually using Toffoli gate as one of the main gate libraries we have so far. And in this process, of course, we have a couple of challenges for which design automation can help. In fact, here we have another example. Here is our AND function. This is an XOR function. And if we want to realize this functionality, we have to make that reversible, because this functionality right now is not reversible, because as you can see, we have two input patterns which actually yield to the same output pattern. So we don't have this one-to-one mapping, which is required in order to realize a reversible function. We can do that. We can distinguish that those equal output patterns by adding further outputs, usually called garbage outputs, because now we can arbitrarily assign them, or at least we can assign them in a fashion so that we get here, for example, the 0 and here 1, and by this we actually can generate two distinguished output patterns. So this is one step. If you're doing that, we now end up with a function which has 3 outputs, but 2 inputs. So accordingly, we have also to adjust the number of inputs. So in this case here, we now have 3 inputs, 3 outputs. That's exactly what we want. Again, we have to accordingly assign those values here so that all those patterns are distinguishable. And because we now got one more input, we also got more input patterns. That means we also have to define corresponding values for all those outputs here. And this can be done, of course, in various fashions, as long as each resulting output pattern is unique and is distinguishable from the other output patterns. And for this example, we can now assign precise values, and except we have lots of opportunities or possibilities here. In fact, in this simple case, we already have 192 possibilities to assign those values. And this, of course, could be an issue, because at the end of the day, we want to realize this functionality in terms of a Toffoli circuit. And of course, the way the cost of this Toffoli circuit, of course, to some extent also depends on how we have chosen all those values here. And eventually, this makes this embedding step already a co-NP hard problem. That means determining the best possible assignment or the best possible embedding in general is actually a very hard task. And for this, design automation tools can help to tackle the corresponding complexity. However, this general approach, as sketched here, has lots of challenges, and it's actually yields actually a couple of drawbacks. In fact, we already discussed about that. Embedding is expensive. It actually is a co-NP hard problem. It's an exponentially hard problem. So this is a serious problem as well. Besides that, if we do embedding before the actual synthesis, we lose a significant amount of degree of freedom, right? Because as said before, in the example before, we had 192 possible embeddings, And we basically, if we conduct embedding separately, we basically decide for one of the possible options, one of the 192 options, and then we just stuck with this single option and synthesize a reversible circuit, although maybe one of the other 191 options might be more suitable for this resulting synthesis step. So if we do the embedding before we do the synthesis, we are losing a certain degree of freedom. And another problem, of course, is if we do this embedding, we increase the function, right? You might remember an example before. We originally started with a 2-input, 2-output function, and after embedding, we ended up with a 3-input, 3-output function. That means the number of truth table entries, or the number of input-output patterns we need to consider, also doubled. And in the long run, this is an exponential growth, which makes the synthesis problem harder. In other words, synthesizing a 2-input, 2-output function, of course, is easier than synthesizing a 3-input, 3-output function. And those are basically challenges. And design automation in the past has worked around lots of solutions how to actually deal with all those challenges, all those issues here. But those challenges have hardly been addressed. And one possible solution to address all those drawbacks here is to conduct embedding and synthesis as one single step, what we call one-pass synthesis. And this is a suitable solution which we can employ here. And for this purpose, let us consider another example to explain how we can actually do embedding and synthesis together. And for this, I'm using existing synthesis approach, which is very well known in the design automation domain for reversible circuits, namely transformation-based synthesis. The main idea here is basically you get an input function, you get an function to be synthesized, in this case, our function from before. And in the original approach, this function was supposed to be a reversible function. And what we are now simply doing is we're taking exactly this synthesis approach and using it with a non-reversible function. That means with the originally given function, not with the already embedded function. And then I will go through those single steps, and then we will see exactly what kind of problems we're running into and how can we solve them. Transformation-based synthesis, the main idea is basically to modify your function so that at the end of the day, you always get the same input pattern as the output pattern, and you're doing that for all the lines. And whenever you reach a line in the truth table where the input pattern and the output pattern are not the same, then you apply Toffoli gates to modify your function so that eventually you end up with the identity function. So, and that's what we're going to do here as well. So, and again, I'm doing it with a non-reversible function. So first thing is we start the synthesis without embedding, and we're trying to map each input to the corresponding output. So we start with the first truth table line, and here we can already see the input pattern is equal to the output pattern, so nothing to do here. And we have the same for this line here as well. And now next, we are considering the third line. And here we are actually seeing not only that the input is not equal to the output, but we run into another problem that here now for the first time, we are actually running into an output pattern, which has been considered already before, right? So this wouldn't happen in the original synthesis approach, because in the original synthesis approach, you would only work with a reversible function. Now we have a non-reversible function, and we're running into this problem. And now before I continue synthesis, I have to deal with this problem first. I have to make this function reversible first in order to continue in this synthesis approach. And here, the purpose is actually, whenever this occurs, we are modifying the function. It means we are changing the function. And in this particular case, I'm simply changing the function by simply inverting this bit here, making it flipping from 0 to 1. By this, I made this function reversible now. But of course, I don't synthesize the function I'm intended to synthesize anymore. I change the function. And because of that, I am actually storing these changes so that I can later revert that in a particular buffer line. That means I'm now introducing this extra line here, which I initialize with 0. And I'm storing that, that for this particular input pattern, for the input pattern 1, 0, we are flipping the value of x. That's the reason why I call this buffer line x. Because this is initialized with 0, and now I'm adding a Toffoli gate that like this, which states when I have x equal 1 and y equals 0, x equal 1, y equals 0, then I'm flipping this x output here, and this is exactly what this line now represents. So in fact, at this position here, this line is set to 1 if and only if exactly such a pattern occurred. And then I know in this case, I flipped my output X, and I have to undo this later on. Using this trick, using this buffer line, I now can continue my synthesis approach because now I have a reversible function. And now I continue my synthesis by making this input equal to this output. And I can basically do this by adding a gate like that. That means whenever X is 1, then I'm going to flip the Y variable. That is basically what this Toffoli gate says. And this is basically exactly as you can see, this is basically exactly what I'm doing here right now. And with this, I can basically make sure that this input now matches this output by adding a gate like that. So I have completed this. And by definition, I also have completed this one here as well. So bottom line, this circuit here now realizes my function, but it realizes the function which I have modified before. And as said, of course, I wanted to realize the intended function, so I have to undo what I've done here before. And this is now easy because I can simply revert the changes I did to the function after synthesis by simply exploiting this buffer line again. Namely, whenever this buffer line is 1, this is the buffer line for the output X. Whenever this is 1, I need to flip X. This is only the case when I have the input 1, 0 based on this Toffoli gate. That means in exactly these cases, this X value is flipped again. And by this, I basically realized my originally intended function. And what I've got with all that is right now, I've got the synthesis approach, which eventually gives me a reversible circuit, but which does not require an explicit embedding step before, right? Because I now can directly, I'm sorry for that. I now can directly realize or conduct my synthesis approach directly on my originally given function, which is a 2-input, 2-output function, and not as stated before with an explicit embedding step where I suddenly generate a 3-input, 3-output function, so a significantly larger function which I have to traverse. Then I have to traverse only 4 two-stable lines, not 8 as before. And I can do that without opting for one of the 192 possibilities I had before. So this is actually a huge improvement. And all that, again, just should sketch the idea. And of course, this one-pass design flow has been also implemented on more scalable functional representations. So here we did it with truth tables in order to sketch the idea, but we also have alternative approaches, which, for example, utilize decision diagrams, which make this whole thing more scalable. And this is just one pitch of how we can synthesize reversible circuits. And as said before, this is just one part of my talk. This was basically the sketch how we can use design automation for reversible circuit. And the second part of my talk, I want to talk about how we can now do something similar for adiabatic circuits. And here I would like to particularly sketch the idea we've done one or 2 years ago together with Mike Frank, which actually came up with some interesting properties for adiabatic circuits, which we can utilize. In fact, Mike Frank showed that full reversibility, as we considered it so far in the design of reversible circuits, are not always necessary. So we might not always need a mapping to a Toffoli gate. In fact, this causes an overhead, which we can avoid because Mike showed that often a conditional reversibility is sufficient. And conditional reversibility simply means that reversibility is sufficient, or that we can realize an adiabatic circuit with some conditional reversibility if we know that we can uncompute a particular result in some cases. And this can be actually realized using certain adiabatic gates. In the following, I just would like to quickly sketch the main ideas. Later in my talk, I will provide, at the end of my talk, I will provide you to some references for further reading, but I hope you will get a little bit the idea on the following things. Because if you just have to respect conditional reversibility, you can actually utilize conventional gate libraries, such as the NAND gate library or the NOR gate library, and you simply employ a two-step approach. You first realize your desired function using your considered gate library, which can again, as said, be NOR gates, for example. And then later on, you just have to map your netlist from composed of this particular gate library to a corresponding adiabatic circuit, which satisfies the switching rules. And as said, let me briefly illustrate that by means of an example. In the first step, we are considering AND inverter graph, which is well known in the conventional logic and where we have lots of design automation tools available for that. And in this example here, we simply did that we illustrate that by realizing these two functions here. So this is an AND inverter graph. The nodes represent AND operations and the edges represents corresponding inputs and outputs. And whenever there's a black dot here in an edge, it basically means the corresponding value is inverted. Now we are basically translating that into NOR gates because we have decided for NOR to be our target library. This can be easily done because every NAND operation and every AND operation can basically be converted into an OR or NOR representation using De Morgan. So by basically flipping or transforming this representation, this NAND representation into NOR representation, we get basically this. And with this, we can get basically an NOR circuit as shown here. And all those steps, this is completely conventional. So this has nothing to do with emerging technologies or with adiabatic circuits in particular. This is just one way of describing our desired functionality in terms of a certain gate library. And now in the next step, we have to map that into a corresponding adiabatic circuit. And for this, we need, of course, to discuss how do we map the gates? How do we map, in our case, the NOR gates into a corresponding adiabatic description? Then we have to connect corresponding power clocks so that we can control the computing and uncomputing. And then we have to generate the corresponding waveforms. So we have the clocks, and then we have to trigger the clocks so that we really trigger the clocks when they compute something and when they have to uncompute something. That's where we need the conditional reversibility. And then, of course, while doing all that, we have to satisfy our switching rules. In this particular case, we have to make sure that at the end of the day, conditional reversibility is satisfied. And now, how can we do that? Again, there's a very straightforward, greedy, naive solution to do that. How to map gates? First, this is easy for OR gates. We basically, for OR and NOR gates, we basically have corresponding transmission gates which can directly be utilized and which can be simply mapped. So for each OR gate we have here, we can basically employ a corresponding set of transmission gates. However, we have to trigger these transition gates with the corresponding clock signals. That means we need clocks. And also here in a greedy fashion, those clocks can easily be determined because we basically can see this circuit here is composed of 4 stages. That means we first have to wait until all the computations of this stage have been completed, and then the results can be propagated to the next stage, and so on and so forth. So in this particular case, how many power clocks do we need? Well, we need 4 clocks because we have 4 stages. And then the question is how to generate the corresponding waveforms. Also here in a naive, greedy fashion, this is straightforward. We have our 4 clocks, and in the 0 stage, we have to first, of course, initialize the computation of the 0 state. After this has been completed, we can use the result and we can initialize the second stage, so this stage here, and so on and so forth. And if all this has been completed, if we have our result, then we basically can undo that, and that's basically where we have to satisfy the corresponding constraints, and this can be done by just doing that in the reverse order. And all that is kind of straightforward, but, and here's where design automation comes into play as well. We can, of course, improve upon that by using dedicated optimization strategies, by using better clocking schemes. And I don't have the time to explain all that in very much detail, but just to show you one further result, we can do all the things I sketched also with this circuit. And as you can see, this is a much more optimized circuit. It is now composed of 2 stages only, and accordingly also we only require 2 clocks, not 4. And then, of course, the corresponding clocking scheme is simpler as well. We also have pipeline-based approaches. So there are a couple of further approaches. And as said, details for that are provided in the corresponding papers, which I summarized here. And this also basically brings me to the end of my talk. Again, this talk was not meant to be a comprehensive overview on many, many technical details, but it should sketch a little bit where we are in the development of design automation tools for reversible and adiabatic circuits. And right now we have these 2 different branches right now. We have lots of work on and lots of tools and methods on the design of reversible circuits using Toffoli gates. And we kind of just started developing first tools for the design of adiabatic circuits. And the bottom line right now is, if particularly, for example, triggered by this workshop, we are seeing that there has been much more progress in the development of both reversible and adiabatic circuits, which yielded better constraints, better models, better objective functions, then I think it is definitely worthwhile to also start developing corresponding synthesis, corresponding design automation tools for that, because you can see the better a technology gets and the more scalable a technology gets, the more important it is to also get support, automatic support with respect to design automation. And I hope this talk here provided a rough overview on that, and maybe hopefully triggered a couple of discussions. Either way, I'm really looking forward to these kind of discussions and to the rest of the workshop. With this being said, thanks a lot for your attention, and take care, and hopefully seeing you soon a minute after this talk. Thank you very much.